Okay, so in this video, we're going to be looking at finding the domain and range of functions and relations. And so we're going to reuse some of the examples I've used in a previous video to determine whether a relationship was a function or just a relation. Now, finding the domain and range of functions and relations in certain forms, it actually doesn't matter whether they're functions or relations, because the domain is just the input values that go into the function, and the range is just the values that come out on the other side, the output values. So, for example, in this case, in this example of a relation, again, we don't really care whether it's a function or not. The domain is simply going to be the list of inputs, which would be A, B, C, D, E, and F. And then the range is simply going to be the set of outputs, which would be red, pink, blue, orange, tan, and white. Now, in the case of a list of points like this, again, it's quite straightforward. If our relation is R, and we'll just spell out range here just to make it really clear. It's just a list of inputs and outputs. So the domain is just going to be 1, 0, 4, 7, 11, and 2. And if you want, you can reorder them so that they are in, numerical order. And then in the range, they would be 4, 3, 2, 1, 9. And then you don't list any repetitions a second time. So even though 4 appears in our coordinate points twice, we don't have to list it twice when we list out the values that are in the output, because 4 is in the output. It doesn't need to be included twice. For a graph like this, again, think about this is just a set of coordinate points in a list. This is the same set of coordinate points on a graph. And so when we list the domain, we're listing all of the values. Here's a 0, here's a 1, here's a 2, here's our 4, here's our 7, here's our 11. Again, in that X coordinate direction. In the range case, again, if you want to list them in order, start at the bottom. And so there would be a 1, a 2, a 3. Here's 4 twice, but only listed one time, and then the 9. Now, in a table, of course, the table is also quite straightforward, because you would simply also say that the list is just the input values, the X, Betty, Pam, Sam, Donna, Warren, and Heidi. And the range would just be the output list: Tom, Toby, Dan, Sophie, Biggs, and Kendall. Now, for more complicated functions where you have, or relations, where you have, like, say, a graph, for instance, or you have an equation, if you can solve it in terms of y, that's great. But if you can't solve it in terms of y, you may also just be able to graph it. So in this case, if we graph this equation, we get this ellipse. And then we can actually see from the graph that the inputs in the x direction are bounded by 4 and -4. So in this case, we don't have a a set of individual values, and so we have an interval because it's a equation of continuous values. It's not a set of points or a set of individual pairs. So here we're going to write this in interval notation. It's going to go from -4 to 4, and then the range is likewise, again, look at the graph. It goes, the bottom number down here is -4, and the top number up here is 4. So the range is also from -4 to 4. Now, when you have explicit equations where x is in terms of y, then we can think about properties of the equation. We can certainly also graph them, but these individual situations are going to depend a lot on the kind of equation we have. So in all of these cases, these are functions, they're defined y explicitly in terms of x. And so for some of these, we have to think about the properties. Now, for a linear equation, the domain is going to be all real numbers, because I can pick any number I want, and I can multiply it by 2, and I get another real number. And then if I take that real number and if I add it to 3, I get a real number. So I can put any number I want into this equation, no problem. The range is likewise all real numbers, because I can imagine, again, this is a linear equation, I can pick any number I want over here, and then I can subtract 3 from it, I can divide it by 2, and I will get some value that I can use to put in to that number. There's no way that I can get sort of a bad value. I can pick any number I want for y, and I will be able to solve for it. So lines have the domain and range are all real numbers. I can put anything on one side, I can put anything on the other. It's all good. Now, for a rational function, the thing that you want to worry about is when is the denominator equal to 0, because that is going to be a problem for the domain. Any value that makes you divide by 0 is not a valid mathematical operation. And so that has to be removed from the domain. So in this case, the domain would have to be x is not equal to -2, because if I put x is equal to -2, -2 plus 2 is 0. I divide by 0, that's bad. Or in interval notation, I would say -infinity to -2 union -2 to infinity. So it's all real numbers except -2. Now, what about the range? Well, for rational functions, the range is a little bit more complicated, but in this case, particularly if you look at the graph of this, you can see there is a horizontal asymptote. At y equals 0. And so the graph never actually crosses y equals 0. It approaches y equals 0, but it doesn't cross it. So here, the range is y not equal to 0, or in interval notation, -infinity to 0, union 0 to infinity. Now, again, rational functions are very complicated. As you start putting more x's into your equation, it is possible that you will cross an asymptote. It may approach an asymptote on the outside, and then you may, in fact, cross it in the middle. Especially if you have multiple vertical asymptotes, that's very frequently happening. There may be actually a range of values that you can't actually satisfy, particularly if you have something like something in the numerator where you have a slant asymptote of some sort. So again, these are very complicated, and one of the things that we will do as we go later into college algebra or pre-calculus is we will talk about other ways of finding out what the domain and range is in relation to the inverse function. But early on, you should be able to graph it and kind of figure out what is going on for at least simple functions. And then this last example, again, something else to think about. We can't put negative values under a square root, and square roots cannot actually produce negative numbers. The positive square root only produces positive numbers. If you want negative numbers, you have to put a negative sign out front of the square root explicitly. So for this one, the domain is going to be essentially depend on x minus 4 greater than or equal to 0, or x greater than or equal to 4. If I move the 4 to the other side. Now x greater than 4 in interval notation is going to be starting at 4 and then going to infinity. And the range, well, as I said, you can't get negative values out of the square root. If you put x equals 4 in here, you will get 0. But then any other value that's in the domain will give you a value bigger than 0. So the range is going to be 0 to infinity. And again, we'll talk about as we make our functions more complicated, as we go through the course, we'll apply various transformations and their impact on the domain and range for the basic function, and then how doing these adding things or subtracting things is going to affect the domain and range as we see it for that particular example function. But early on, again, some basic properties of common functions you should still be familiar enough with. And again, if you graph these functions, you'll see that there are no values for this function below the y-axis, and the graph starts at 4 and then goes to the right on the graph. It doesn't go to the left on the graph. And so you can fall back on your graphing strategies to help you figure out what is going on with these functions.